To analyze the behavior of currents and voltages on a transmission line, we mathematically model the line as a sequence of lumped circuit elements. Considering a small segment of the transmission line of length delta z, we include series inductance and series resistance, modeling the inductance and resistive losses of the conductors. We also include a shunt capacitance and shunt conductance, which model the capacitive storage and leakage through the dielectric. Each of these elements are a per unit length, multiplied by the change in space delta z. This means that the units of meters cancel out, and we are just left with our inductance, resistance, capacitance, and conductance along delta z. We define the input voltage as a multivariable equation of space and time, VZT, and we define the output voltage with the same equation but shifted by delta z in space. Our input current travels along the top wire, and can be modeled in space and time like our voltage. Because we are working with delta z, a small length of wire, we can now use Kirchoff's voltage law to come up with some equations. Using Kirchoff's voltage law for this first loop, we can produce the following equation. We can algebraically manipulate this equation so that our delta z terms are only on the left side. We then let delta z approach 0, and the left-hand side of this equation becomes the definition of a derivative. This is our first equation. We can then use Kirchoff's current law to obtain the following equation. Notice that conductance is equal to 1 over R, the current through a capacitor is C dV dt, and the final branch is just our space-shifted current. If we take the limit as delta z approaches 0, we end up with our second equation. These equations are coupled first-order partial differential equations, known as the Telegrapher's equations. In order to solve these equations, we need to create a single second-order PDE. Let's start by taking the derivative with respect to z of our first equation. We now need to find terms to replace del I over del z and del squared I over del t del z. Let's try taking a derivative with respect to t of our second equation. We can now substitute these two terms into this equation and create a single second-order partial differential equation. We can algebraically now simplify our equation. This is known as the wave equation, and solutions to this equation give us the voltage at any point in time or space along the transmission line. Now, in order to solve the PDE, we can express our voltage in Phasor notation using complex numbers. In Phasor notation, time derivatives become multiplication by j omega. We can now plug these complex equivalents into our original wave equation. This will greatly simplify the derivatives in our equation and give us a time-harmonic equation, which allows us to temporarily remove the explicit time dependence. After simplifying our time-harmonic wave equation, we can make a substitution and replace this constant on the right-hand side with gamma squared. This is the complex propagation constant squared. We are then left with a simple second-order differential equation. The general solution can be expressed as V0 plus e to the negative gamma z, plus V0 minus e to the gamma z. Now that we've arrived at our solution, what does this physically mean? Well, let's remember that gamma is complex. Therefore, it can be expressed in terms of its real and imaginary parts. Gamma squared is equal to a bunch of real and complex constants. You can see that all of the real terms of gamma come from resistance and conductivity, while our complex terms are attached to the inductance and capacitance terms. The first term in our solution represents the forward-traveling wave going in the positive z direction of our t-line. For lossless lines, the decaying exponential term with alpha goes away, because r and g are 0. This leaves us with a forward-propagating sinusoid. The second term in our solution represents the backward-propagating wave going in the negative z direction. The lossless wave also looks like a sinusoid. As a quick recap, transmission line theory is a more accurate model that takes into account factors that become more prominent at higher frequencies when wires are electrically long. We use this T-line model to come up with a partial differential equation, and then solve for the time harmonic voltage. Our solution is made up of a complex and decaying exponential term that shows us how resistance, conductance, inductance, and capacitance determine the shape of our sinusoid, and whether it's lossless or not. I've shown you the Phasor form of this solution because it is what is most commonly used. Remember that there is still an e to the j omega t term, but it is usually implicit. You can also express the solution in terms of all real numbers, which would require deriving the real part of the complex exponential using Euler's formula, and arriving at this solution.